We will focus on the property analysis tools in Aspen distillation synthesis. Before diving into the Azeotrope search and ternary map features, let's get an overview of the binary mixture analysis. Typical results for this analysis include the TXY diagram and the YX diagram. In the YX diagram, the crossing of the y equals x line indicates the existence of an azeotrope. We can enable an azeotrope search from the analysis group as well. Given valid phases, components, property methods, and necessary binary parameters, a search for azeotropes can be performed under specified pressure. Under Output, you can obtain the boiling points for pure components and azeotropes formed from a selected mixture of components at a specified pressure. One of the most useful tools is the Ternary Map, which can be created via the Properties Environment Analysis group. The typical plot is like this figure. On the left side, you can input the desired pressure and then press Enter to recalculate the map. The View panel allows us to hide or show various objects on the ternary plot, such as azeotropes and distillation boundaries. The three peaks of the ternary plot show the boiling point of pure components. The distillation boundaries are denoted by green lines with an arrow pointing from low to high temperature. The residual curves are displayed with blue lines. The azeotropes are denoted with red diamonds, and the corresponding temperature is shown as a data label. The composition at the location of the mouse is shown on the upper right corner. The toolbar allows you to add markers or curves for analysis, rotate component coordinates, flip components, and toggle the grid of the map. The function of each item can be seen in the tooltip by moving the mouse over the buttons. The ternary map can be used to analyze a column for possible products. Mass balance dictates that the top and bottom products must lie on a straight line through the feed point in the diagram. Therefore, for this ternary system with a feed composition of 30% IPA, 30% acetone, and 40% water, if the desired distillate is pure acetone, then the bottom is on the red line. If the bottom is pure water, then the distillate is on the black line, but not beyond the distillation boundary. The ternary map can also be used to check if a separation sequence is possible. The system includes three components: water, acetone, and IPA. Is it possible to separate water in the first column and then the two-component system, acetone and isopropanol, in the second column? With the pure water from the bottom of the first column, the distillate composition is on the black line containing a mixture of all three components. Therefore, the best the second column can reach at the bottom is in the azeotropes shown in the red circle with about 70% IPA and 30% water. Based on previous data, we can conclude that this sequence is not feasible. To overcome the boundary, you can change process conditions, typically the operating pressure of a column, or add entrained components. Both methods will change the ternary map such that the boundaries are adjusted or disappear. This demo investigates the separation possibilities for an acetone-water MEK mixture using ternary maps. The file has four predefined components: acetone, water, MEK, and methanol, and a selected property method of NRTL-HOC for the analysis. We assume that binary parameters and data are good and well represented in this system. First, we will evaluate binary azeotropes using binary analysis. From the Home tab in the Properties environment, click Binary from the Analysis group. We will do a binary analysis of a water MEK system, so keep the default settings for components and compositions. The calculation basis will be the mole fraction. We want to evaluate across different pressures to see the impact of pressure on possible azeotropes. So, enter values 1, 3, and 6 bar in the pressure section. Click Run Analysis. From the TXY plot, we can clearly see the azeotrope moving as pressure decreases. In practice, pressure swing distillation is one approach used to avoid an azeotropic distillation boundary. A second approach is to add entrained components. Create a second binary analysis with the same components and compositions. Set pressure as 1 bar and enable the pseudo-binary system option to evaluate methanol as an entrainer. Add an entrainer mole fraction of 0.0, 0.2, and 0.4. Run analysis. We cannot see the impact of methanol on the azeotrope from the TXY plot. Let's check the YX plot instead. The YX plot clearly shows the azeotrope moving with more methanol added as an entrainer. Binary analysis of a 3-component distillation system is inadequate to effectively find azeotropes. Let's explore the capabilities of Aspen distillation synthesis to do ternary analysis. In the Home ribbon, click on Ternary Diagram under the Analysis group. Click Use Distillation Synthesis Ternary Maps. Later, we will investigate the separation possibilities for water MEK acetone system, so let's keep the components as default. Change pressure to 1 bar. Do not calculate residual curves and the vapor-liquid-liquid envelope. Click Azeotropes under Output. Notice an MEK water azeotrope will form. Click Ternary Plot. The azeotrope is shown on the map as a red diamond. Note that the distillation boundary is a result of this azeotrope. Now suppose we are given a feed of 15% water, 20% MEK, and 65% acetone to design a separation scheme reaching a distillate of 97.9% acetone, 1.9% water with 99.9% acetone recovery. We would like to investigate the separation possibilities of this mixture using ternary maps. First, let's put the feed stream onto the ternary map. Click Add Marker by Value from the toolbar and input the composition of the stream. As we can see, the feed stream is very close to the distillation boundary at 1 bar. The separation is difficult in this situation. Therefore, we propose a pressure swing distillation scheme with 2 columns. The first column, operated under high pressure, separates pure MEK as a bottom product and a mixture of all 3 components as the top product. The second column, operated under low pressure, then separates the distillate of the first column into pure acetone as overhead and MEK water azeotrope as the bottom product. Let's see how to represent this scheme on the ternary diagram. The first column is operated under high pressure 6 bar. Add a line to represent the first column starting from 100% MEK, passing over the feed toward the distillation boundary. The intersection point of the first column and the distillation boundary is the distillate of the first column, which will be feed of the second column. The acetone composition of that point is about 78% reading from the ternary map. The second column is operated under low pressure at 0.7 bar. Add a second marker representing the distillate composition of the second column, 1.9% water, 0.2% MEK, and 97.9% acetone. Add a line to represent the second column starting with the second marker, passing over the feed toward the distillation boundary. With this scheme, we can now develop a conceptual design of this separation scheme.